Hello and welcome to the second part of graphing derivatives. For this particular session, we're going to see how to take the derivative of a function and graph its second derivative, as well as taking that and drawing the original function that it has. So as you see, we have three graphs here. We're going to start off with graphing the first derivative to second derivative, and then we're going to go back to do the first derivative to the original function. And so this will give us practice sketching derivatives both going quote unquote forwards and backwards. So to start off, since we're trying to sketch the graph of the second derivative, then we know that the original function for the second derivative is the first derivative. So we're just trying to track the slopes of the tangent lines here. So first thing that we want to ask ourselves is, where are the horizontal tangent lines on the graph of f prime? So we see that here's a place where that happens, and we see that another place where that happens is here. So essentially where our peaks and or dips are on the graph. We notice that the slope of the tangent line of the graph here is at 0, but to the left of that it is negative. To the right of that, they are positive. And at this point, to the left of that, the slopes of the tangent lines are positive, and to the right of it, they are negative. So what that communicates to us, if we're looking at the graph of the second derivative, is that here, where we have horizontal tangent line, and that will be at x equals -3, that will communicate that the graph of the derivative of the first derivative has got to be at 0. And this tells us that the graph has to be drawn below the x-axis before this point and above the x-axis after this point. So our graph would have to look like this. Similarly, at x equals 1, we see that we have another horizontal tangent line, and the slopes are positive before, negative after. So this tells us here at x equals 1 that the graph of the derivative has to be drawn above the x-axis before the point and below the x-axis for after. So here we can kind of see that this graph is sort of going to have a upside down parabolic shape. The last thing that we need to do is figure out where this peak is going to be at. And so of course we don't know exactly what value or y coordinate is going to be, but we can at least guess the location or where the x value, where that happens in. And so if we look, as we talked before in the first video, our inflection point should be somewhere in here. And so I'm going to put it about right here, which is at the x equals -1/2 point. And so here, when x is equal to -1/2, if we trace that down, this should give us about right here, where we could have that peak in the graph. And remember that this inflection point is communicating that the slopes of the tangent lines, as they get more and more positive at that point, they stop getting more positive and then turn the other way. Okay? And so with that, we have the general profile of what this particular graph will look like. Okay? So now with that, we'll go ahead and move on and work our way backwards now. So now we have the first derivative and we need to draw the original function. Well, our thinking here needs to be exactly backwards. So before we said, where are the peaks and dips in the graph so that we can draw the x-intercepts? Well, now we look at the x-intercepts, and then from there we see where the peaks and the dips of the original graph are. So looking at that, we can see that, and I'll go ahead and erase these out of the way here. We see here that at this particular x-intercept, the graph is drawn above the x-axis before and under afterwards. So that tells us here at this particular x value, which I think is at x equals -5, we are going to have a peak in the graph. So I'm going to put my point here, and we have a peak there. And of course, we know that here the slopes of the tangent line are 0, and of course, we know that happens here. This says slopes of the tangent line are positive, which we know that happens here. And on the right of this point, slopes of the tangent lines are negative, so that fits that. We do the same thing with the other x-intercepts. So we have one at -1. So this maps up to when x is equal to -1 here. And notice that the graph is below the x-axis here, up to the left of the point, and above. So that tells us here that the slopes of the tangent lines are going to be negative before and positive afterwards. So if I pick this point here, we'll see slopes of tangent line are negative before, negative slope. Slopes of tangent line are positive afterwards, positive slope. So we have a dip in the graph. Looking forward here, if we move on to x equals 3, we see that we have another situation where the graph is drawn above the x-axis to the left of the point and below the x-axis to the right of the point. And so that's communicating to us that we have another peak in the graph. Okay, so we go here and we can find us another peak. I'm going to make it interesting and come up here this time. And we'll find ourselves another peak in the graph. Okay. And so from this point, we kind of have an idea of the general shape. It's going to look something like this, but we need to figure out where those inflection points are. And so if you remember from the last video that the inflection points were communicating the place where the slopes of the tangent lines stopped getting more negative or more positive. And so here in this case at x equals -1, -2, -3, we see that the derivative stops getting more negative here, which means that if we go map up, that means that the slopes of the tangent lines here stop getting more negative. And so we'll pick that inflection point to be about right there. So that means we'll go ahead and draw a line like that. Similarly, here at x equals 1, we see that the graph of the derivative stops getting more positive. So that means that the slopes of the tangent lines in the original graph stop getting more positive. And we'll estimate that point to be about right there. And so we would draw the graph like that. And so with that, we see that we got a general profile of how the graph would look. And now we can just trace it out. So see, it looks like this. Come down to this. And we fill it out. And so of course we're able to draw the graph like that because we know that the derivative of the graph is a continuous function. And its domain is all real numbers. So the original function has to be a continuous function. And the second derivative also has to be a continuous function. And its domain also has to be all real numbers. And so with that, this concludes the second part of graphing derivatives.